this computer. Yes, okay. So we have been setting up the stage actually to solve this problem, essentially, using quantum mechanics, because this is the this is the most paradigmatic system that we are going to be seeing and or solving using quantum mechanics, and what we've been doing before is just explaining how you set up an equation that actually makes sense for the physics that we're going to get out of the hydrogen atom. So the hydrogen atom is simply a proton, which is something close to 2,000 times the mass of the electron that is sitting in a place, and the electron is moving around. Okay, but this motion around the nucleus of the proton, which can be described with these variables r, theta, and phi, is something that we want to describe not using Newtonian mechanics or Bohr model. We want to use it, solve it using the Schrödinger equation and see how does it look. Okay, so what we have seen before is that I think I have something missing here. Yeah, I do have something missing. What we want to do is solve the Schrödinger equation in 3 dimensions. And that means we have to add to the kinetic term, which is h minus h squared over 2m times the Laplacian, in this case, the derivative with respect to, the second derivative with respect to the variable x, y, and z of the function phi. And let me be bold here and add what I need to, and this is equal. I don't know why this is equal to E, the energy of the system, times phi. Okay, so this would be the Schrödinger equation that we are interested in solving. We want to see this wave-like behavior of an electron is actually well described by this Schrödinger equation. That does it provide reasonable numbers out of it? And if I measure things in an actual hydrogen atom by some means, I should get something that makes sense with this. Okay, so that's the question. That's what we want to solve. Okay. Okay, this is strange. Why I'm here? Let me go to. I don't know if this will work if I do this. Okay. Now I don't see you, but you see the whole.
I mean, technically it works, but it looks a lot smaller than before.
Oh, okay. I'm not gonna do that. Yeah, I've seen this happening before. And how do I do this? I escape from here and go back to this. Usually, I show you the PDFs of the PPT transparencies, but because in the Mac somehow when I use presentation mode, it overtakes everything, and I don't understand exactly what happens. It has never worked as it should in Zoom, essentially. So let's well, the E times phi was here. I cut the thing, so this thing is gone now. We don't need it. And let me go back to using. Can I use the spotlight? Yes, I can. Okay. So this is what I want to solve. This essentially. This nabla square is simply taking each one of these terms here. This is essentially the thing that I want to express. Nabla square means these derivatives here. And with respect, twice the derivative with respect to x, y, and z. Sum in the way they are done there, this is symbolically represented by the same thing here, okay? This is an operator in math. This is Laplacian operator. This Laplacian operator can be written in Cartesian coordinates as the one that I wrote you before, because this is the way we started. This is the way we know this equation. But in this particular case, we also know that the symmetry is of the x and y z axis makes little or no sense whatsoever. Meaning the actual variables to actually describe this problem should be the radius and the angles, the radial coordinates, because that's the natural symmetry of the system. Okay.
I'm guessing we have to find a way to transform it into the radial components.
There's you know, the mathematicians do this very well. They have this Jacobian thing, and they do these transformations, and lo and behold, they get what they want. Or we can do it one by one, because we know exactly how to write. Essentially, x is r times sine theta times cosine phi. So if I can write x as a function of r, theta and phi, I could actually write this derivative and you know, go through the whole thing of the partial derivatives in terms of changing the coordinates that I actually need. I have 3 coordinates here, and I can replace the x, y, and z by r, theta, and phi. You know, and I'm not going to do that because it takes forever to actually do that. But here are the equations. But I'm getting a bit ahead of myself. The first thing here is that this mass that I have here, if this is the mass of the electron, that will require that this particular proton here is actually nailed to the system of reference. And we know that that's not the case, because the proton can also move. You know, what really is not fixed in space. Actually, if there's no force, is the center of mass of this system that is in a resting position. Okay, but let's assume that's the case, that the center of mass is in a resting position. So essentially, when the electron moves, the proton has also to move in order to maintain the same position for the center of mass. Okay. When one does that in the proper way, this mass here have to be changed to something like the reduced mass. The reduced mass of a system of 2 masses is something that you actually probably, you know, found in the first course in mechanics. Is 1 over the reduced mass is equal to 1 over the mass of one of the particle plus 1 over the mass of the second particle. But since the mass of the second particle is 2,000 times the mass of this particle, you know, I didn't even bother to put an R here, you know, which is a mistake. Okay, legally this should be the reduced mass of the electron. Okay, that's one of the caveats. The second one is I want to write what you were saying. We have to find out a way of writing the x, y, and z as a function of r, theta, and phi, okay, which are the reasonable variables in this case. Why are they reasonable? Because look at the shape of the potential. You know, I have something that is 1 over the square root of x squared, y squared. Wow, forget it. You know, you're never going to solve anything. And with this coordinate system, you have to use something that is, you know, has a higher degree of symmetry in order for you to get the functions out. What is the thing that has the higher degree of symmetry? This is exactly 1 over r. So that is telling me that I should write this part of the coordinate as r, theta, and phi. Okay, and not only that. So I don't not only write the nabla square, but I also use separation of variables. Okay, I said, look, the same thing that I did with the system with the square well in 3 dimensions. What did I do? I said phi is equal to x of x, y of y, and z of z. Okay, big letters. And the idea of doing that is because that's a natural way to separate the equation. The natural way to separate the equation is this one here. Something that's only a function of r, only a function of theta, and only a function of phi. And you replace the proper operator nabla square in here, and argue, what do we do next? Well, these are the equations that you get. Okay, I'm just reproducing what the books is telling me. So I have a second order differential equation here. This is the second order, the two derivatives of a function of the radius. I get this this solution here that it gives numbers L plus 1 times 1 over r squared. If one looks at this thing here, this could be interpreted as kinetic energy again, because it's twice the derivative of something that can be oscillatory. This term here is added to the potential somehow, and look at the shape it has. This thing here on top have units of momentum, square of the momentum angular, of the angular momentum divided by r squared. Okay, so this thing over here is a potential barrier. It's a centrifugal barrier, meaning you add something to the potential simply because the particle that you are looking at has some angular momentum. And I'm going to come back to this. This is the interpretation that this value over here is the solution to this equation. From this equation, you get the L plus 1. And when you introduce it here, you get this thing here, that this term is exactly equal to what you will get in classical mechanics if what you have on top here is the square of the angular momentum. Okay. There's a lot on this on each of these solutions, but and actually the fact that this thing is actually L plus 1 has something to do with the symmetry of this equation, and you have to really find a solution that is convergent, and you can present the solution to this theta equation as a series. So the series needs to end at one point, and for the series, the need for the series to end requires that this constant that I use here should be written in this way, because otherwise the series will not end. And this is also a separation of variable constant between the r and the theta. So that's why the L and L plus 1 appears in this equation and in that equation. Okay. Going through the details of this is probably 4 or 5 lectures on itself. Okay, and I'm not interested in you guys doing that at this point. I just want you to understand what the solution is and what is the road to get there. I don't want you to work all the details in this thing. Okay. There's the third solution, that is this equation over here, which is very nice, because this we know how to solve this. This is simply, this is a periodic function on phi, and this periodic function of phi the solution should be something like this. Y should be something like this, because as I showed you before, this thing has a periodicity of 2 pi. So if I change phi to phi plus 2 pi, I should get the same solution. okay? So with that boundary condition imposed on this solution, I find that phi of phi plus 5 plus 2 pi has to be the same. So I know then that the solution is of this form e to the im phi, okay, where m should be an integer. Because if it is not an integer, you don't get this condition on top here. So it has to be an integer in order for this thing to work. Okay. From the first equation here, we obtain two things. We obtain, for example, if we solve this equation, we obtain two things. We obtain first of all, this is the equation for the energy. This is for this thing, we actually obtain the energy of the hydrogen atom, of the energy levels of the hydrogen atom. Here's the energy. And R is the amplitude, the probability amplitude of finding a particle, meaning R squared will be the probability of finding the particle in a certain radius. When I mean R squared, I mean the capital R squared, okay? So if I square that, it will give me a 2 alpha R here, A times A conjugate, whatever it is. So what does this give? This gives a dependence of the radial probability. So essentially this decays exponentially with R, and the decay constant, this decay constant alpha here, should be proportional to 1 over a characteristic length of the hydrogen atom. That characteristic length is actually the Bohr radius, which we found when we were discovering the Bohr model. The Bohr model works very well and reproduces most of the experimental data, and so does this description that is completely different in conceptually. Okay. Now we're thinking of electrons as waves. Okay, and before we were thinking of a particle circling around the nucleus with a certain angular momentum defined by, discrete ways as multiples of h bar. And with that, we can generate the spectra of the hydrogen atom. But there was no good reason for that to work actually in general. And now we have an equation, and we're going through the boundary conditions, and we're finding the same solutions. Actually, if we look at the energy is exactly the same expression. So this is a great coincidence that the two models, one based on conceptually different properties, they produce the same results. So the energy levels for the hydrogen atom then is a constant, which is E squared times, I wrote the reduced mass just in case, 4 pi epsilon naught squared, 2h bars. Everything here is well known, okay? Mass of the electron, constant of the universal constants, and the charge of the electron. And this here is a number, 1 over n squared. And the first number that you can find here is 1. And as soon as these numbers start to increase, the energy is closer to it's closer to 0. These energy levels are negative. It means that the particle is actually, the electron is actually bound to the nucleus. That's a negative energy. 0 energy will mean the particle or the electron moving freely up to infinity. Okay, that's the longest thing. Okay, so we have this expression, when I replace all the constant, gives you exactly the same expression for the energy as the Bohr model, as I told you before. Okay, we can define something like solving this equation. This equation here, I could actually express it as a function of L squared. the angular momentum square. I can express this equation as the angular momentum square. And if I do that, and I solve that equation, I find that the eigenvalues of L squared are integer values of H. Well, not exactly integer value of H, but L squared is integral values of H squared multiplied in this way. So if L is integral, L squared can be written this way. It will be an integral value if L is a bit large, it's a large value of L. If a large value of L, this is equal to L squared. So L is equal to H times an integer, essentially. That's what it is, okay? But in quantum mechanics, we get this. This is sort of surprising because, you know, when we were looking at the particle in a box, given the boundary conditions of the particle in a box, we found out that the energy levels are quantized, meaning not any energy level is valid solution for a certain well potential or an infinite well potential of a certain size. There's only a discrete number of energy levels, and the levels are actually scaled somehow with the length, okay? If the length is very narrow, meaning the energy levels are highly sparse, you know, but somehow you have the feeling that there is a natural confinement that gives you the solution that the energy in this case is quantized. Here, there's no quantization, there's no restriction to the angular momentum in any way. The angular momentum is naturally quantized in this system, okay? As in the way that I can write an operator for kinetic energy and an operator with respect to you know, linear momentum in terms of complex derivative, you know, that, let me go back here. No, let me go back here. If I want to recognize that this thing here is equal to P squared over 2m, this kinetic energy term here, I have to recognize that the momentum can be written as minus I h bar, the gradient of the wave function. So if I interpret that as the operator and I square that operator and divide it by 2m, I get this expression, okay? So I can define a quantum mechanical expression of an operator that mimics the kinetic energy, and I have one that mimics the linear momentum in 3D. I can do the same thing with the one that mimics the angular momentum. And the solutions that I have for that, this is a complex operator. I can put a wave function here. The wave function corresponds to this theta thing. And I could, you know, write them up in this way, and this will be equivalent to this equation, to solving this equation, okay? So if I move this thing over there, I'd actually have to multiply it by phi too, but you know, let's not get complicated here. You know, this is okay. So this expression here means that the angular momentum of an unconfined system is quantized. That's nature. You know, the angular momentum is not continuum, it's quantized naturally. And that is, when you really think about it, it could be a bit shocking, you know, because there's nothing, it's just the space that is actually quantizing the angular momentum. Great. The good thing is that it happens that it works. The possible values of L that I could put in this equation are 0, 1, 2 to n minus 1. This is you see here is a departure from the Bohr model, because in the Bohr model you could not have L equal to 0. L equal to 0 will mean the particle will be resting, and we know that we cannot have a resting particle. So it's completely peculiar to actually find out a way that there exists a wave function with no angular momentum that is actually a solution to this equation. Okay, and the reason why we can have that, and it's not something that has zero velocity, it is you know, it's not actually something that is at rest with respect to the nucleus. It is simply because the wave function means that you can interpret it as a probability density. So there's a probability of finding the particles in this or that space, and that somehow takes care of the fact that you can have an L equals 0 solution. Okay. These are rules that are very difficult to follow. You just take my word for it. And now the value of M, which is linked to this L value here, goes from minus L to plus L. Okay, so for each value of L, there are 2L plus 1 possible values. Okay, minus L to plus L, 2L plus 1. Okay. So if I start looking now to the different levels in the system, you know, this is how it looks. Let me see if I could, yeah, put it in here. So we have, this is the value n. So if the value is n equal 1, the only possible value of L could be is 0. Why is that? Because L, I wrote it somewhere, I didn't say it gets only to n minus 1. Okay, so if n is 1, the only possible value of the angular momentum is 0. So the ground state of the hydrogen atom is it has a series of quantum numbers which can be defined by this number here. The value of n is equal to 1, the value of L is equal to 0, and if L is equal to 0, ML has no chances but being 0. Okay, so the N, the L, and the ML are as such in the ground state, and in spectroscopic notation, the value of L, as I'm showing here, the values of L are actually assigned letters. Instead of saying an L equals 0 state, we call it S. With L equals 1, we call it P. With L equals 2, we call it D. With L equals 3, we call it F. So this S stands for sharp, this for principal, this for diffuse, and this I forgot. No, not for forgot. I forgot what the F means, but you know, it's somewhere in the book it is, okay? And then G stat for nothing, you know, is the next letter. They run out of imagination to actually name them, and then they follow the alphabetic order only. Okay, so and so that corresponds to n equal 1, 2, 3, 4. Those are the n levels, and the L levels that goes to 0, 1, 2, and so on. Those can be interpreted as angular momentum state SPDF and G, and then the actual layer the electrons are, the layer are called N, and in the first layer, second layer, third layer, fourth layer are labeled by the letters K, L, M, N. Okay, for those, and the reason for that is historic. For simply for spectroscopy notation, meaning something that people did before quantum mechanics actually discovered that there were some bright lights coming out of these elements, and they labeled with those letters. Okay, so this would be a K state with S equal it would be an S state and with no component of the angular momentum, actually. If this is the case, you know, I didn't write this down. If L is linked to the modulus of the total momentum of the system, angular momentum of the system, the ML is linked to the Z component of that angular momentum, which is also a quantized quantity. And I'm going to get to that in a minute, okay? So let me go back to this. In the case of n equal 2 now, I have the possibility that L could be equal to 0. Okay, this could be equal to 0 because it's less than n minus 1, but it can only go up to 1 because n is 2 minus 1 is 1, so L can go from 0 and 1. If L is 0, the only possibility of M is being 0 because it only gets there. But if M is 1, I have 3 possibilities for ML. It could be minus 1, 0, and 1, okay? This level over here is called then, this is the layer is 2, the second layer, and the angular momentum of the electron here is 0, so it corresponds to an S state. This is 2 also, but now I have a P state. I have an L equal 1, so it's a P state, okay? So this guy is a 2P. And the shells here are labeled like that. This is the K shell, this is the L shell, the M, and we'll stop at the end, you know, at the 4th level. And then there are other letters for the other ones, but these are the ones that are really important from the point of view of transition, especially when it involves generating X-rays from these materials. And we will touch that you know, later in the next classes. Okay, so this is the great thing out, and there's some uncertainty here. Why is this L linked to this ML? And as I mentioned before, this L is linked to the size of the angular momentum, and this ML is linked to the component of the angular momentum in the Z direction that we have chosen, okay? Let me go back here and speak about angular momentum, okay? So the angular momentum is quantized. This is what I told you before. L is equal to the square root of L times L plus 1 times h bar. So the minimum unit of angular momentum is h bar. H bar is the way the angular momentum increases. Okay, so and L can be any of those values. What I mentioned here, interestingly, in our solution on the Schrödinger equation, there is an L equals 0 solution that is valid. This is not the case in the case of the Born model. Okay, and also one can define an operator linked to the Z component of the angular momentum. And that operator linked to the Z component of the angular momentum is simply minus IH time derivative of the wave function with respect to C. With respect to theta. Okay, so actually I can write this equation here, I can write this as a function of as an eigenvalue problem from LC. In the same way that I wrote this equation here, I can write this equation here as an eigenvalue problem for L square. I can write this equation here as an eigenvalue problem for LZ. Okay, and as you may imagine, LC has something to do with the spatial derivative with respect to phi, meaning, let me get to the diagram here. So the this is the z-axis, this is the phi axis. So the L component of the wave, the LZ component of the wave function has to do with the whatever solved the eigenvalue problem with derivative with respect to phi. If I make derivative with respect to this thing, and you can see it looks like something going around like that, it gives you a component of this of the momentum, of the angular momentum in this direction. Okay. If not very precise what I have just said, you know, there is some link between those two aspects that could be made a lot more formal than what I've just said. In the diagram to the right, what I'm showing, oh God, yeah, in the diagram to the right, what I'm showing is what are this is a diagram from an angular momentum which is equal to the value here is 2. So it's 2 times 3, so it's the square root of 6 times h bar. So that would be the maximum value of the momentum for this particular thing. And if it is 2, it has 5 possible values or components of LC, and this is what is somehow shown in this diagram. So this is one projection, this is the other projection, there's a 0. So the ML could be 2, 1, 0, minus 1, minus 2, and correspond to this angular projection of the angular momentum along the z direction. Okay. You know, we have two types of diagram here. See the you know, you can get something that has the right z component if this value of the angular momentum is actually rotating around the z-axis as shown here. Okay, so not only the angular momentum is quantized, but also the z component of the angular momentum is quantized, and this is sort of with the graphical representation that I'm giving you here. Okay. Now, let's go back. I think I miss. Yes. Yeah. So this thing should be here, I think. It would be the sensible way to do. Let's talk about now about electron probability distribution. Where does the electron lies? Because we're saying the thing that you can actually measure is the wave function square. You cannot measure the wave function. You can measure the wave function square. The wave function square is a measure of the probability where you can find an electron around the nucleus. Okay, so phi square is that probability, and you can actually numerically integrate, or not numerically, you can actually do it you know, in the functional form if you know the way P of R depends on anything. So here I have P of R. This is the probability, the differential probability of finding the electron between the coordinates R and R plus dr. Okay, so in any sort of tiny vertical line in this graph, what is that? It is simply the value of phi squared multiplied by this contribution, which is the volume contribution. Where does this come about? Well, because this is not a one-dimension thing. This is a radius. Okay, so that is the corresponding thing that we're seeing here. The other important value that one has to keep in mind is that the actual scale length of decay of this wave function, as I told you before, this is an exponential decay. The length scale for decay is given by A, and A is simply the Bohr radius. So in atomic units, length should be measured in Bohr radius. That's what it is. Okay, so it doesn't really account for more. the Bohr radius is roughly half an angstrom, according to this, and you can see how the probability distributions of this particle look at this. This guy looks absolutely centered in the middle of the radius. But if you go and plot this phi square corresponds to the 2s state. Okay, let me go back to S state. I'm looking at the 1s state. That's the ground state. The 2s state is the layer L with the zero angular momentum. So it's 2 and S. So it's exactly this state over here. So this is the 1s and the 2s, and I'm comparing. These are the closest state in the system, in the hydrogen atom. And let me go. No, let me go here. No, let me go here. And this is the way they look. Okay, this is centered above the radius. This guy here is you can see that there's a region where there's a very low density to finding the electrons. You find it close to the nucleus, and very well separated. Most of the if I integrate this probability, it is higher to actually find it here than to find it closer to the nucleus. Okay, this looks here very similar to this guy. Okay, and this part is what we mostly associate with the external part of the wave function. Okay, so if you have an atom in the ground state, and I could ask you, please calculate the probability of finding the atom, 1 angstrom away from the proton, okay, in the hydrogen. What would you have to do? Well, you will have to integrate this function from 0 to, in this unit, probably a factor of 2, because the Bohr radius is actually equal to half an angstrom. So if I set to 1 angstrom, so is the area under the curve here multiplied by 4 pi r square. I have to get the phi, put it here, multiply by phi, and integrate this between 0 and 1 angstrom. Okay, and it will be the area under the curve here multiplied by that factor. So this is the sense that one should get about what is the meaning of the electron probability. The darker the areas here is the higher the probability to find them. Look that there are nodes. This guy has a node here and here. This is a 3s. This is a 2s, has 2 nodes. This is the 1s, no node, only infinity. Okay, the infinity node. This is 2s, 2 nodes. This is one of the zeros here is at infinity, and here I have an intermediate one when it's 2, and when it's 3, I have 3, 1 here, there, and at infinity. Okay, so the other 0 here on the function is at infinity, and you can see that. Well, you cannot see here, but let's see the 4. This is the 4. This is 1. It's 1, 2, 3, and then it has to come up, and the axis didn't go that far, but this is the way it works. Okay, so I can graph the radial probability for L equals 0, L equals 1, L equals 2, and so on. And well, clearly for higher numbers here, you also have to change the layer. The layer here, this is an M state. The 3D is an M state. Okay. This state here are L equal 1 states. You get the 2p, 3p. So all these state all these layers, the second, third, and fourth, can have states with L equal to 1, okay? Because for all of these, L is equal to or less than n minus 1. In only this case, it saturates. I mean, in this case, you cannot have angular momentum higher than L equal 1 because you are in an L layer, okay? So this is the things that one has to look in detail here to understand the solutions. Probably, you know, if there's something one has to understand is this way of labeling things. The angular momentum increases this way. The total angular momentum, the z component of the angular momentum increases this way until the double the value of L. This, the modulus of the angular momentum, total angular momentum can increase until n minus 1, where n is the actual layer in which the electron is living, okay? So this thing here is what really one has to know. And then you have to learn how to label the states in this way. So as soon as you get to for example, here, the fourth layer, well, in the fourth layer, you can have angular momentum 0, angular momentum 1, angular momentum 2, and angular momentum 3. So instead of having two lines as you have here in this case, you have two lines for the L shell. In here, you have 3 lines for the M shell. You'll have 4 lines for the N shell, okay? And so on, okay? So the number of states keep growing as a function of energy, as a function of the number N. And you have to realize that for this particular, for this atom, the hydrogen atom, the energy is only a function of N. So this is a single energy, but these states with L equals 0 and with L equal 1 in this model also have the same energy because they correspond to the same N. So here, how many states do I have? I have 1 here, 2, 3. I have 4 states associated with N equals 2. Okay, with N equals 3, I have how many this is? 4. So here I have 1 for this guy, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Wow. So somehow this looks like 9, n square. 2 is 4, n square again. So if I take this number and raise it to the power 2, I get the number of the degeneracy of the states in the hydrogen atom. You could try to prove if that is the case and why. But it's an interesting equation. And the fact that there is degeneracy has to do with the symmetries that the system has in 3 dimensions. Okay, let me go now to consider a perturbation to this system. Let's have a hydrogen atom and turn on a magnetic field. If we turn on a magnetic field, what it will happen if the atoms are, and for doing this you know, simple model, I will go back to the Bohr model because it provides good, reasonable approximations. If I apply a magnetic field, the electron has a charge, and the electron is moving around the nucleus. So it has a component of the angular momentum. It's like it's generating a current as it goes around the nucleus. And this is simply Bohr model. Okay, so one can think of an electron generating some sort of a loop of current by moving in this trajectory here. Okay, So this particular loop will have a magnetic moment, which is simply equals to the current in the loop multiplied by the area. This is the magnetic moment, and the magnetic interaction, the magnetic energy of a system like that is simply minus the magnetic moments times the magnetic field. Okay, so this is the expression for the energy, which means that if I put this, if I have a loop, a macroscopic loop, for example, in a magnetic field, what will that happen? Well, the thing is, the coil will feel a torque, and it will go to the position of minimum energy, and the position of minimum energy here will be align the magnetic moment with the electromagnetic field applied. So this A vector here should point out in the same direction of B. And this is the minimum energy because mu and B will be aligned. So the minimum energy is when they are both aligned, and that is the position when they are happy, you know. Let's estimate based on this simple model to describe the magnetic moment of an electron as the one that is obtained by the electron actually traversing around the nucleus in some sort of a circular motion. We can estimate the Zeeman energy, which is the energy added to the electron, apart from whatever energy is given by the potential energy of the nucleus. The fact that I turn on a magnetic field, I will add some energy to the system. I says, how much energy are you adding? So let's assume that applying a magnetic field doesn't change actually the trajectory. Okay, it produces a very small change in the trajectory of the electrons because the magnetic field is weak enough compared to the electric field that is holding the nucleus together, meaning the electron and the proton together. So the magnetic moment is essentially the current times the area. And I could think of the current being equal to the current of the electron, the charge of the electron divided by the period it takes to go around in one cycle, because that's essentially a current. A current is the charge that passes through an area as a function of time. And this is going to be the charge that passes through an area as a function of time. What time, a period, what charge, one electron, okay? And I have to multiply that by the area. This is pi r squared, okay? And you know, I can decompose this thing a bit more, write it like 2 pi r times r divided by t, and a factor of a half because I put that 2 there. But I can recognize that 2 pi r divided by t is the velocity of the particle that goes around. It's 2 pi r is the length it's actually going through in what time? In time t. So this is actually the velocity of the particle around the nucleus. Okay, so I just write it as b times er over 2. Okay, but you know, I want to now write this expression of the magnetic moment as a function of the angular momentum. Why is that? Because the angular momentum is a sensible quantum number, not the velocity. Okay, so I write the L here as, this is the simple Bohr model for the thing MRB, and I replace this by RB divided by M is equal to L, and I do that. So essentially, I generalize this to the expression that the magnetic moment of an electron would be minus E. Why minus E? Because it is a difference if, with respect to the angular momentum, if the electron has a positive or a negative charge. It has a negative charge, the sign of the current is changed. So with respect to the angular momentum, the position of the angular momentum. So this is the right vector equation. And it happens that this vector equation is not only good for the Bohr model that I use here, it's also used for the Schrödinger picture, okay? So when I do that, I could actually find out that I think I have it over here better, yeah. Yeah, probably this is misplaced again. Okay. Okay, so we have this expression for the magnetic moment, but we know that L is quantized. Okay, so we know that L is quantized. So this is going to be the thing. And if this is the thing here, I replaced essentially the modulus of the magnetic moment by a factor which is a number. Okay, it's a number that could be the square root of L times 1. This is a number, so an integer number, times this factor here, because the only thing that I did from here to the next is replace this by square root of L times L plus 1 times h bar. So the unit of magnetic moment is essentially E h bar divided by 2m. This unit, E h bar divided by 2m, has a name, okay? This is called the Bohr magneton, okay? It's the actual units of the magnetic moment of an electron in an atom. And everything, all the magnetic properties of any nuclei, not only the hydrogen atom, is measured in unit of Bohr magnetons, okay? So this is one Bohr magneton, and one Bohr magneton is 5 times 5.8 times 10 to the minus 5 electron volt per Tesla. So you can imagine that one Tesla is a fairly big magnetic field. You know, I can put a hydrogen atom in a 1 Tesla magnetic field or 10 Tesla magnetic field. It's a huge field in terms of whatever I do in experimental physics. It gives an energy. Imagine this is 5.8 times 10 to the minus 4. So the amount of energy, how does this get? Well, you know, I'm getting ahead of myself here, you know, because the energy of the magnetic energy interaction is equal to mu c times b, perfect. And essentially I could write it down like this, like minus mu b times ml, with m is equals to these values, and well, this is the value of mu z. This is the magnetic moment, and if I replace the magnetic moment in this expression here, which is the same as here, I can write it as ml mu b times b. This mu b is this guy over here, and b is the magnetic field. And this is the value that I was telling you before. If this thing is here, 5.8 to 10 to the minus 5 electron volt per Tesla, and I have a field that is a huge field, about 10 Tesla, this product over here in terms of energy will be only in the range of a fraction of a milli electron volt, okay? It's a tenth of a milli electron volt compared to the energies of the electrons in the hydrogen atom, which are of the order of electron volts. The ground state is minus 13.6 electron volts. So applying a magnetic field to an atom just changes a tiny bit the energy of each of the levels, and the size of the change is this one. Okay, that's the message. And how small is this? It's very small. So my approximation that actually the actual wave function of the atom is nearly unaltered, but just simply modify or rearrange a bit, it's a good description. Okay. If I look at the systems here, you have to see that the magnetic effect of an atom Okay, I'm almost done. Okay, if oh God, how can I speak too much? Okay, so this is the shape that actually the energy, the additional energy of applying a magnetic field produces in an atom and gives you is proportional to ml. So if ml is 0, this is 0. So you have to get a magnetic quantum number, which is a component of the magnetic of the angular momentum along the z-axis, which is aligned with the B in this case, where this is where the B is. The magnetic field is aligned along the z-axis. You get this expression, and this number can only change the energy levels of the unperturbed hydrogen atom by this tiny amount, which are, you know, a few times this value. Okay, this was my whole point, and this is explained here. And so in the case of this is a proper energy diagram now, because this is the ground state. The ground state is right here. So if I apply a magnetic field from an atom in the ground state, the ML for that state is 0. So no matter how high the magnetic field is, I cannot change the energy level of this guy. The same thing happens with the L equals 0. All the L equals 0 states are generally unperturbed. Okay, so you cannot modify the energy levels of the hydrogen atom by applying a magnetic field when they are in the L equals 0 state, when they are in an S state. But what happens when they are in an L state? Well, when they are in an L state, you know, I have this expression that tells me that there is a change in the energy level, and the change in the energy level is proportional to the value of M, and this thing is, you know, the magnetic field times a constant, okay, which is the Bohr magneton. And in this case, we have 3 levels because we have 3 components of the magnetic field. One that is aligned and counter-aligned. And looks what happened. The lowest energy state is the one that has -1, which is, it means that the electron should be, the magnetic moment should be counter-aligned with the magnetic field, okay? So this is why the smallest number is at the bottom in all this thing. The negative values are at the bottom. It's the least energy. So here, in the case of L equals 1, which are these states that I'm showing here, these are the L equals 0, these are the L equal 1 states. I have 3 states for all the layers, and you can somehow split the energy level that was. All the states were here, and now they are split a bit. There's a difference between them. And these guys, they are also different. And now here you had 3 levels, and here you have 5 levels, okay? And let me see, do they show here what, you know, you should be able to estimate what is the intensity of the magnetic field used to show this diagram. Because you can see the difference from this level to this level is around 0.85, okay, 0.7. So the difference, if the difference between this level and that level is actually 0.7, and in those 0.7, this is probably 0.65 from the center axis to that point over there, you can actually estimate what is the separation between 2 levels here. And if you estimate the separation, you're gonna find out that this is a huge magnetic field that you have to apply to have a difference in the energy levels like this. It's probably more, it's larger than 100 Tesla to actually make a figure like the one that is being shown here. It's being shown like that just to show by clarity that you can split the levels in the way they are, okay? But it is really you having a superconducting coil to actually produce a field this high. I don't know if there's anything that I don't know if people can get to to produce over a wide area a range of probably they do a magnetic field that intense, but it has to be in pulse mode. They can only go whack, very high and then they drop it down. So very instantly they can produce a field that is as high as this. But you cannot have a steady state magnetic field which is as high as this one over here. You have to remember, for example, the MRI machines are 1.5 Tesla, and that's very, you know, reasonable technology, and they cannot get to 3 Tesla because doing that change, applying a constant magnetic field in a localized region of space, it's something that is very expensive to do. Okay, so if they don't do in the medical profession, they don't do in science either. Okay, so this is the way it is. I'm not going to say anything about selection rules. I'm going to mention them briefly next time. I think this is enough for today. Okay, so please read everything about the hydrogen atom. I don't know what to ask here, but probably, you know, learn about probabilities. Everything that you will be required to calculate, I will give all the information for you to do that. But you need to know what you need to know here. You need to know the L values, the M values, and the conceptual thing of what the probability means in this particular case. Okay, so this is sort of the elements on the hydrogen atom. Okay. With that being said, this is it. I hope you're awake, Ismael.
Yes, I am.
You are, okay. So this is it. This is the class for today. We'll see each other on Tuesday. Okay.
All right. Take care.
Okay. Enjoy the weekend. Ciao.